Hi everyone, my name's Miles and I'm going to talk about our paper Primal Dual Descent Methods for Dynamics. This was work that was done in collaboration with Kenny Erleben at the University of Copenhagen and my colleagues at NVIDIA, Matthias Muller, Chentanez, Stefan Jeschke and Taeyong Kim. The motivation for this work comes from looking at two different methods for implicit time integration, projective dynamics and position-based dynamics. And I refer to these as primal and dual methods, respectively, and I'll talk a little bit more about where that label comes from. But the questions that we're trying to answer in this work are, how are the two methods related? Is there some common mathematical basis for them? How sensitive are they to different forms of ill conditioning? And can we extend projective dynamics to large-scale rigid body simulation? This is something that's usually the domain of constraint-based methods like PBD. So just to give some mathematical background, one way of phrasing implicit time integration is as an optimization problem. This is sometimes called variational implicit Euler, and it's the form taken by projective dynamics. Here we have an objective G that consists of two terms, an inertial term, which is a quadratic form, and an energy potential, which gives rise to forces. And the goal is to minimize G with respect to some system coordinates. So in projective dynamics, this is written in terms of positions, Q. Here I've written it in terms of a generalized velocity, U. And this is a simple reparameterization, but it's really convenient when we come to deal with rigid bodies that have a linear and an angular component. So our time-stepping update, given this, is u plus the velocity at the end of the time step, is just the solution to this minimization. And then the system coordinates, the positions, can be updated directly by evaluating this kinematic mapping that relates the angular velocities and linear velocities to the coordinates, which might be positions of the center of mass and a quaternion orientation. So how do we solve this type of minimization? The methods that we consider in this paper are all descent methods. So here the idea is to start with some guess at the solution and repeatedly take steps along the negative gradient, maybe with some precondition of p. And how we choose p has a pretty big impact on the method that we get. So if we choose p as the Hessian inverse, we get a Newton method. If we approximate that with quadratic potentials, we can get a Gauss-Newton method. And the method that we focus on most closely in this work is the method presented by Wang et al., which is a diagonal approximation of this Hessian. So this gives rise to a Jacobi-style method, and they show that actually this is in fact a special case of projective dynamics. So how do we get from this primal optimization problem to something like position-based dynamics? The first step is to split our energy potentials into two parts, a constraint function C and some Lagrange multipliers lambda. And when we do this, we can write down something called the Lagrange dual function, and then this gives us a dual optimization problem. So we're no longer minimizing G with respect to U, we're now maximizing H with respect to lambda. And it's not immediately obvious how this relates to something like position-based dynamics, but if we look at how we actually solve this dual maximization problem, we'll see how these relate. So one way to solve these dual problems is something called dual ascent. And here the idea is to take a step first on the primal variables by performing this minimization, keeping our Lagrange multipliers fixed, and then taking an ascent step on the dual variables. And if we approximate that primal minimization with a linearization, then and follow that by an ascent step with a diagonal preconditioner, we get back to XPBD. And so we can think of projective dynamics as solving this primal optimization and PBD as solving this dual maximization problem. So I think this is really nice. It gives us a common variational framework for thinking about the two methods. And it does give us some more insight into how they behave. So we can look at the conditioning of these two problems and make some predictions about how these different solvers will converge. And in this case, one way to get an idea of the conditioning is to look at the Hessian of the problem. And if we assume for the moment that K is very large, the norm of K is much larger than the mass matrix, then we can essentially disregard that in our analysis. And likewise, in the dual problem, when K is large, the inverse of it becomes very small. So we have a small compliance matrix and we can ignore that. Then what's left is going to dominate our conditioning. And for the primal problem, that's this matrix K. And what this means is that when K is ill-conditioned, then the primal problem will be ill-conditioned. K is our stiffness matrix that contains the stiffness coefficients of our potentials. On the other hand, for the dual problem, M inverse is now going to dominate our conditioning. And what this means is that when we have large mass ratios, for instance, we have a very ill-conditioned dual problem, and it will be hard to solve. So we designed some experiments to test this. In this case, we have a large mass ratio where we have a heavy body attached to a much lighter one. And we can see if I let it run, the primal solver is relatively unaffected by this. It gives us a nice stiff response. Whereas in the dual method, we have a lot of excessive stretching, and this is essentially a residual error that results from using a fixed number of iterations, and we use the same for both methods. So this is in line with our analysis on the previous slide, but it was a little surprising to me, at least to find out that these primal methods are so relatively unaffected by the mass ratio problem. On the other hand, if we look at a stiffness ratio, in this case we have a very stiff link at the bottom attached to a much weaker link at the top. And this actually gives rise to a stiffness ratio that causes the primal methods to converge very slowly. On the other hand, the dual method is quite unaffected. So what is essentially happening here is that the stiff link at the bottom is causing the link at the top to converge very slowly. And this, again, it's in line with our analysis, but a little surprising because I think that the stiffness ratio sensitivity hasn't really been identified or discussed very much in the literature. And we can get some more intuition about why we see this effect just by looking at the condition number of the system. And as we increase the mass ratio, we see that this condition number for the dual problem goes up, and we have the exact mirror problem for the stiffness ratio case. As we increase it, we see that the condition number for the primal problem goes up. And so this explains why we see this slow convergence. So that's really the first half or one of the first contributions of the paper, to try and give a common mathematical background for the two methods and to analyze the sensitivity. And I hope this gives a little bit of additional insight into how they behave in practice. For the rest of the talk, I want to switch gears a little bit and cover contact and talk about how we extend these primal optimization frameworks to rigid body contact. So first I want to start by looking at the dual contact, because this is really, I think, the more common approach for multi-body dynamics, where we introduce these hard contact constraints to prevent interpenetration between bodies. And this gives rise to a complementarity problem that is relatively easy to fit into our dual methods. So essentially, we can enforce this complementarity constraint by projecting our Lagrange multipliers onto a positive cone after each of our iterations. The question is, how do we adapt this to our primal methods? Because there we have an unconstrained optimization problem. And so in the paper, we propose a relaxed contact model. Here you can see on the force profile on the right, for an exact solver, which is a complementarity-based method, we see that the force can lie anywhere on the vertical axis around the origin. In our relaxed model, we replace this with a hinge function where the steepness or the slope is controlled by a parameter kn. And this essentially controls how much interpenetration that we're willing to tolerate between two bodies. And we can exponentiate this model to obtain a smoother force profile. And this is useful when we come to consider things like differentiable simulation. I'm going to touch on that briefly, but it's also nice because this primal form allows us to fit in any arbitrary force model. For example, some Hertzian model is quite easy to fit into this form. This is just one sort of example. And really, there's a large class of implicit penalty methods. I think that penalty methods have a little bit of a bad rap in graphics because I think they're often paired with explicit time integration. But in fact, when they're paired with an implicit method, they can be really effective, and I'll talk a little bit more and show some examples of that. Similar to interpenetration, we can relax our Coulomb contact or Coulomb friction model. And here you can see in the force profile on the right, when there's zero slip, we have a force that can lie anywhere inside the Coulomb cone on this y-axis. When there is slip, we expect the force to lie on the cone itself. And we relax this by replacing it with a step function where the slope around the origin is controlled by a parameter kf. And essentially this controls how much slip we allow, because now what this means is that there's always some residual slip, even there's no frictional forces unless there's some tangential slip. So this can be derived from a non-smooth potential that we give in the paper, but we can also smooth this using some other smooth potentials, such as a pseudo-Huber norm, or something like tan H can also be used. The question that we want to answer, the questions we want to answer are, can these penalty methods of contact achieve a similar accuracy to our tried and tested dual methods? Are they stable for large time steps? How do the sensitivity problems that we identified in the first half manifest when we're talking about contact? And then there are some secondary issues like what is the effect on things like force distributions and differentiability. So this example was inspired by some work by Zhu and Barwick from 2014, and they simulated a similar scenario using an implicit method with a direct solver. And we found that we can simulate the same thing using our descent-based methods and scale it up to many more contacts. So in this scenario at the end, there's around 400,000 contacts, and this is still real time with our descent-based methods. The interesting thing here is that the two methods actually perform pretty similarly, and this is a bit of a surprise, but in some ways expected, because there's no real source of ill conditioning. There's no mass ratios or stiffness ratios present. But we see that the Primal solver actually does a pretty good job of forming a stable pile. A little more interesting example is when we have some ill conditioning. And in this case, we have a large mass ratio of around 80,000 to 1 between the granular material and the weight on top. And we see that the dual solver has a lot of compression at the start, while the Primal solver is relatively unaffected, so it gets this nice stiff response. A less obvious problem with the Primal models of contact is that in this case we have a large interpenetration stiffness, so a large Kn, and a relatively smaller Kf, but it should still be sufficient to achieve a stable stacking. But when I let it play, you can see that we get this artificial slip in the Primal solve from the Primal solver, and this is essentially a residual error that results in this artificial slipping. So the takeaway from this is that if you're using this type of contact model, you want to set your normal and your frictional stiffness values to something that's quite close in agreement. I think this was around 100 to 1 ratio between the two values, and it does create these more difficult problems. This example was inspired by a paper from Soller et al. At SCA a few years ago, and they identified a problem with position-based dynamics in the context of Cosserat rods. And they found that they couldn't achieve a certain stiffness past some range. And so in this example, the cloth has a very high stiffness coefficient of around 10 to the 10, and so we would expect to see very little extension as it falls under gravity. But what we see is that the dual method actually does have a lot of sagging, and this happens even without the contact scenario with the cylinder on top. And we identified this as being a side effect of the approximate primal minimization in our dual ascent method. So the analysis we did in the first half helped us, I think, to understand where this actually comes from. And replacing that approximation with something a little more accurate would help address this. Another question that we wanted to answer is, how do these primal and dual methods, these models of contact, behave with respect to things like force distributions? Often in simulation, we have a constraint Jacobian that becomes rank deficient. And what this means is that there's more than one valid solution. So an example of this is the cylinder resting on the ground on the right, where we have a ring of contacts, and both of these visualizations would be valid solutions that lead to the same acceleration on the body, but they're very different in the way that the forces are distributed. So what we see on the right is something like you might get out of a Gauss-Seidel solver, where the distribution is essentially random. But often we want a nice smooth distribution of forces. For example, when these are inputs to other methods, such as a neural network controller or audio synthesis. And there have been works that have actually addressed this by explicitly redistributing contact forces onto around the surface. And what we found is that actually these relaxed models of contact do this automatically. So you can see on the left, the primal model of contact has a nice smooth force distribution, and the one on the right, which is a dual method, has a really noisy distribution. So this is a nice side effect, I think, of these relaxed models. Another question we had was, how does this residual error with the friction, how does this relaxed friction model deal with things like stable stacking? And this is a classic example of a house of cards. And we found that actually the primal methods, again, do fairly well, surprisingly well. Even though there is some residual slip and it will eventually collapse without some additional history-based tracking, they can still achieve pretty nice results. Another example of this is a grasping scenario here, where we have a robotic gripper, and you can see that as the stiffness, if we use a low stiffness coefficient for the friction parameter, we get this artificial slip. But if we set it appropriately, we can get results that are pretty much on par with a dual-based solver. Another consideration that I mentioned was differentiability. We have this nice smoothed contact model, and so we can use that to perform things like trajectory optimization. And in this example, the goal is to learn an initial velocity, and we're optimizing it using LBFGS. And the goal is to hit the target, the black box, through these two contact events. And this converges pretty quickly in around, I think, 30 or so LBFGS iterations using this smooth contact model. So just to summarize the trade-offs between these primal and dual models of contact, one advantage of the primal model is that when there are many fewer DOFs than constraints, for example, like in the figure on the right, we may have thousands of contacts but only 6 degrees of freedom, the primal model gives a much smaller problem to solve. It also remains constant in size over the course of a simulation, provided we're not adding and removing bodies, which is another nice property. The primal methods are mass ratio insensitive, and they're pretty easy to extend to arbitrary nonlinear contact models. We found that they give good force distributions, and they can be made differentiable quite easily. The disadvantages are that you do need to pick these stiffness coefficients, and the ratio needs to be within some range to avoid creating these stiffness ratio problems. For future work, an obvious extension would be to apply accelerated descent methods. These are almost as simple as gradient descent, but they can have much faster convergence. In addition, the original Projective Dynamics paper used prefactorized matrices. In this work, we've focused on Jacobi methods because they're well suited to parallel architectures, but the extension to prefactorized preconditioners would be interesting. The other question here is how important is smoothness of our contact and force models on things like trajectory optimization? I think we need some more experiments to really understand the interaction between smoothness and optimizers like LBFGS. So in summary, we've presented a unified view of projective and position-based dynamics through a variational lens, and this has allowed us to perform a sensitivity analysis and get some more understanding of how these methods respond to different forms of ill conditioning. We've extended projective dynamics to rigid body contact and benchmarked it on a number of rigid body contact problems, and I think we've shown that primal methods of contact can be really effective. With that, I'll finish and leave you with some references, and thank you for listening.